Section 22.11 Butadiene, Cyclobutadiene, and the Cyclooctatetraene. First, 1,3-butadiene. In 1,3-butadiene, the 4 p orbitals, one from each carbon, forms conjugation. So you have these 2 occupied pi orbitals, and these 2 are empty pi star antibonding orbitals. All 4 can interact with the transition metal. These 2 are occupied, therefore they donate electrons to empty d orbitals. These 2 are empty, therefore they accept d electrons from the transition metal. And when you do the interaction between this MOs with the transition metal, make sure that you match the symmetry of this MOs and the symmetry of the d orbitals of the transition metal. For example, over here, if you look at the 1, 2, 3, 4, the bottom 4 lobes, they have the same phase as this one. This is in phase, and this is constructive interference. And electrons can flow from this 1 pi orbital to the dz squared orbital. And same here. Although there's a 1 nodal plane in the middle right here, that means this 2 and this 2 are out of phase. Okay, this 2, this bottom 2, this 2 are out of phase, but still they can interact with a different d orbital, in this case dzx orbital. And because in dzx orbital these 2 lobes are out of phase, so let's say this red is positive phase, and then these 2 bottom lobes are also positive. So these 3 will interact with each other in a constructive manner. These 3 are all negative phase, negative, 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 and they can interact with each other in a constructive manner. So again, this 2 pi orbital may donate electrons to this empty dzx orbital of the transition metal center. Now let's look at these 2 empty orbitals. They can also interact with the d orbitals centered on the transition metal, but they are going to accept electrons. So now let's look at this 3 pi orbital. It's right here, and then this is occupied dyz orbital. This 2 are positive phase, negative phase, and over here positive, positive, negative, negative. And then of course between this pink and this 2 yellow, there's constructive interference. And between this red and this 2 brown, there's constructive interference. And then this electrons from the dyz orbital can be delocalized into the empty 3 pi orbital. That reduces the electron-electron repulsion and thus is favored. Finally, this one. Same here. You need to have constructive interference between the lobes of this dxy orbital and also the bottom 4 lobes in this 4 pi orbital. Then electrons can flow from this dxy orbital to the empty 4 pi orbital of 1,3-butadiene. 1,3-cyclobutadiene. This is a very interesting case. It has a ring structure. It has 2 double bonds, and you observe single bond, double bond, single bond, double bond. But this is not aromatic. This is not aromatic. The 2 double bonds are almost like isolated double bonds with this kind of MO diagram. So you have 1 double bond on the left, 1 double bond on the right. In between, you have 2 single bonds. Okay, same here. Single bond, double bond, double bond. And the 2 double bonds, again, are not conjugated. Over here, pi star on the left, pi star on the right, pi star on the left, pi star on the right. And also, there's no interaction between this pi star and this pi star. There's no interaction between this pi star and this pi star. There's a reason for that. If you try to make this conjugated 1,3-cyclobutadiene, you will not observe the aromatic property. It's actually anti-aromatic. In organic chemistry, you might have learned that if you have a carbon ring with a number of double bonds and single bonds. If you have, for example, in this case, 1, 3 positions, so you have double, single, double, single. If you have a total of 4n electrons, integer multiple of 4, this ring structure is anti-aromatic. It's not stable at all. And if you have 4n plus 2 such p electrons in the conjugated network, it's aromatic, for example, benzene. And 4n plus 2 can be 2, 4, or 10. So if you have carbon 3H3 plus, it's aromatic as well. If you have, for example, carbon 5, hydrogen 5 minus with 2 double bonds and 1 CH minus anion, and then it's also aromatic. So now let's get back to this. What if we force this 2 double bonds and 2 single bonds to be conjugated, and then you have this MO diagram, and then you have 2 degenerate orbitals. 2 pi and 3 pi are degenerate. And supposedly you need to put 2 electrons here, and actually supposedly you need to have alpha spin and alpha spin here. Alright, but this 1,3 cyclobutadiene can be aromatic if it accepts 2 electrons from the transition metal. And then you have 6 electrons. That's 4n plus 2. It can also be 4n minus 2. So if this cyclobutadiene loses 2 electrons to the transition metal, and then there are only 2 p electrons left. And in this case, this 1,3 cyclobutadiene with 2 plus charges can be aromatic as well. And now let's look at the interaction between the d orbitals and this MOs. The most important part is the match of the symmetry. Over here you have this red lobe from the d orbital interacting with the bottom 4 brown lobes. Okay, they're in phase. Same here. You just need to make sure that the interacting MOs match. The symmetry should match. Or you can say their phases should match. So again, they can interact with each other. There can be electron flow from the metal to this 1,3 cyclobutadiene or backward. Either way. If you have empty d orbitals and if these 2 are occupied, well, then electrons can flow from these 2 pi orbitals to the empty d orbitals. And if you look at this MO diagram, well, they are both partially filled, so it's possible for the electron flow in both directions. It can go from metal to this ligand or from the ligand to the metal. And either way, you can convert this anti-aromatic property to aromatic property. And over here, again, there's interaction between the metal and this 4 pi orbital, as long as you match the colors properly. Now finally, let's talk about a much larger ring structure. This is Cyclooctatetraene structure. So again, you have a ring structure with 8 carbons, and you have 4 double bonds, you have 4 single bonds in this ring structure. If you draw a planar structure with a D8H point group, and then it's going to be anti-aromatic with 8 p electrons in the conjugation network. It's not stable. So in the real world, the structure of this carbon 8, hydrogen 8 is non-planar. This is just to break the symmetry, to break the planar structure, to break the conjugation, to prevent this structure to be anti-aromatic. And then in that case, you will very likely observe either 4 isolated double bonds. You may observe 4 isolated double bonds. Okay? And another possibility is you may observe something like 2 separated 1,3 butadiene. So you can have 1 butadiene, 1,3 butadiene here, and over here you have another 1,3 butadiene as well. And this cyclooctatetraene structure has 4 double bonds. If the orientation is right, it may donate all p electrons to the transition metal center. That's eta 8. But also it's pretty common for this cyclooctatetraene to donate only 4 p electrons to the transition metal, and this is eta 4. Over here, this is eta 6. So 6 carbon atoms are the 6 points of attachment in this complex.